In the previous section, we discussed an engineering problem where simulations can be used to answer how many bolts are needed to achieve proper sealing in a pressure vessel. Based on the results, we recommended that more bolts are required to achieve proper sealing. In this workshop, let's revisit this problem, make the recommended changes, and see if this new design meets the criteria. Here's the new design. It has 8 bolts of same dimensions. As you can see, the bolts are modeled as solid bodies with circular heads. The pressure vessel and the fasteners are made of structural steel, and the gasket is made of graphite material. The threads are not of interest, so we simplify the threaded portions and use bonded contacts between the nut and the bolt. We use frictional contacts between all other mating parts. We will fix the bottom vessel and use a bolt preload of 100 Newton in each bolt. Bolt pretension object is used to define the preload in them. We will then apply a 100 Newton force on the top plate to mimic the force applied by the pressurized fluid on the plate. Since there are no inertial effects in the system, we will solve this as a static analysis. For this problem, we will perform a parametric study to perform design iterations by varying the bolt diameter and see its effect on the seal performance. Let's start setting up the model. Open Ansys Workbench and set the unit system to be the metric unit system. Then import the workbench file called bolted vessel, which contains the parameterized geometry. If you double-click on the parameter set, you will see that there are 4 parameters that we can define: the nut diameter, the bolt diameter, the hole's diameter, and the outer diameter of the bolt heads. In this model, only the bolt diameter is an independent parameter, while the other 3 parameters are dependent on the bolt diameter. So, we only need to define the bolt diameter here. Let's keep the value of the bolt diameter unchanged at 0.75 millimeters. Go back by closing the tab for the parameter set. Since this is a static analysis, we drag and drop a static structural system. Then, we drag the geometry and drop it in the Model tab of the system to indicate that we wish to use the geometry of the bolted pressure vessel for our analysis. Next, we define the required materials. Both the materials are modeled as linear elastic materials. The structural steel is defined by default, so we only need to define graphite material. To create a new material called graphite, go to the toolbox on left and under Physical Properties, double-click on Density. Define a density of 2.25 into 10 to the power minus 6 kg per millimeter cube. Next, under the Linear Elasticity tab, double-click on Isotropic Elasticity and define a Young's modulus of 28,269 megapascals and a Poisson's ratio of 0.17. Now let's open Ansys Mechanical. The first thing we do is to check that the units are consistent with what we chose previously in Workbench. Then we assign the materials to respective bodies. By default, all the bodies have structural steel assigned to them. We only need to change the gasket material to graphite. In order to manage the large number of bolts and nuts and to create contact pairs in a systematic manner, we will first create name selections. Make sure that Select Body option is active. Hide all the parts other than the nuts and the bolts. Using the box select mode, select all the bolts. Right-click and choose Create Name Selection. Let's call this name selection Bolts. Next, use the Select Face option to select the lower surfaces of the bolt heads. Following the same procedure as used previously, create a name selection called Bolt Head Spacing. Select the surfaces of the bolt shanks and create a name selection called Bolt Shank. Next, activate the Select Body option, select the nuts and create a name selection called Nuts. Then using the Select Face option, select the upper surfaces of the nuts and create a name selection called Nut Spacing. Now hide all the bolts. Select the inner surface of a nut and create a name selection called Nut Grip. While creating this name selection, choose to include items of the same size, same type, and having the same location C. This will ensure that inner surfaces of all the nuts are included in Nut Grip. The bolt and nut surfaces come in contact with two other surfaces of the pressure vessel. So, we create name selections for these two surfaces as well. We create a name selection for the top face of the upper plate and call it Top Face, and another name selection for the bottom surface of the other plate called Bot Face. We now have all the surfaces between which contact needs to be defined. Next, we will define contacts between various components. Ansys Mechanical automatically detects and defines bonded contacts between surfaces that are close to each other. So first, we delete all these initial contacts and then create them in a more controlled manner. The first contact pair we create is frictional contact between the top plate and the gasket. Insert a manual contact region. Use the Select Face option and choose the lower surface of the top plate to be the contact face and the upper surface of the gasket to be the target face. Specify the friction coefficient to be 0.2. We need to create a similar contact pair between the gasket and the other plate. So duplicate this contact pair. Choose the lower surface of the gasket to be the contact face and the upper surface of the bottom plate to be the target face. Next, we will define contacts involving the bolts and the nuts. In order to avoid repetition of steps, we will use Object Generator to create contact pairs. Insert a connection group and then insert a manual contact region for that connection group. Choose the lower surface of one of the bolt heads to be the contact face and the upper surface of the top face to be the target face. Define this contact to be frictional with a coefficient of friction of 0.2. Under the Definition tab, change the behavior of the contact to be asymmetric. To generate similar contact pairs between the top plate and the other bolts, go to the Automation tab and click on the Object Generator. This is where the named selections that we created earlier come in handy. For the named selection to use as contact side, choose bolt head spacing, and for the target side, choose top face. Next, we specify the minimum and maximum distance between the centroids of the components for which the contact pairs will be created. Let's keep the minimum distance to be 0 mm and the maximum distance to be 5 mm. Change the scoping method to all entities by path. Since we use a single surface as the target side for all the contacts, if we ignore the original pair, no contact pairs will be created. To avoid this, unselect the Ignore Original option. When we click on Generate, we see that no additional contact pairs were created. This indicates that the limits we specified for the distance between centroids are probably too conservative. So we increase the upper limit to 10 mm. Now we see that additional contacts are created between other bolts and the top plate as expected. Since we unchecked the Ignore Original option in the Object Generator, we manually delete the original contact that we created. We repeat this procedure to create frictional contact between the nuts and the bottom plate. The nut surfaces are defined as the contact faces, while the bottom plate is defined as the target face. A coefficient of friction of 0.2 is used and the contact behavior is set to asymmetric. When we use the Object Generator, nut spacing is used as the contact side, while bot face is used as the target side. All other options are set to the values used in the previous case. We again follow a similar procedure to create bonded contacts between the bolts and the nuts. The inner surfaces of nuts are defined as the contact side, while the bolt shanks are defined to be the target side. The contact behavior is set to asymmetric. The trim contact is set to on with a trim tolerance of 1 mm. When we use the Object Generator, nut grip is set to be the contact side and bolt shank is set to be the target side. Let's try setting the maximum distance between centroids to be 0.5 mm. We see that no new contacts are generated. So we increase the upper limit to 2 mm. Now we see additional bonded contacts being created between other nuts and bolts. Notice that we did not have to uncheck the Ignore Original option in this case, and so we do not need to manually delete any contact pair. Now that we have created all the contact pairs, the next step is to mesh the assembly. Let's set the element size to be 0.5 mm. Next, in order to get a uniform mesh, we select the pressure vessel and select Insert method. We change the meshing method from automatic to hex dominant. We saw in the previous section workshop that bolts are best meshed using a multi-zone method which divides the bolts into multiple zones and tries to mesh them in a uniform manner. So next, we select all the bolts and change the meshing method to multi-zone. Then we generate the mesh. Next, we apply the boundary conditions and solve the model. Since this is a problem involving preloaded bolts, we need to have two steps. In the first step, we will apply the bolt preload, and in the second step, we will lock the bolts and apply the force on the top plate. So under analysis settings, we change the number of steps to 2. For the first step, let's set the auto time stepping to on, the number of initial substeps to 5, the minimum substeps to 5 and maximum substeps to 100. Repeat these settings for the second step. In addition, the large deflection should be turned on for step 2 since this is the step when the actual load is applied on the assembly. Next, we want to fix the bottom vessel. To do this, select the bottom surface of the vessel and insert a fixed support boundary condition. To mimic the pressure on the top plate, we insert a force boundary condition on the inner surface of the top plate. We will define the force by components and define a Z component of -100 Newton so that the force acts in the outward direction. Keep in mind that this force of -100 Newton is applied in step 2. Step 1 is reserved for preloading the bolts, and so the assembly should not be loaded simultaneously in step 1. So we deactivate this load in step 1. Next, we apply preload to the bolts using the bolt pretension object. To do this, we need to define a local coordinate system whose principal plane will be used to define the location where the bolt is cut. The cutting plane must be within the grip length of the bolt and must not pass through the region where bonded contact is defined. Let's say we want the bolts to be cut by the mid-plane of the gasket. To define a local coordinate system, choose the upper and lower circumferences of the gasket and insert a coordinate system. A coordinate system is created whose XY plane coincides with the midplane of the gasket and whose Z axis is parallel to the bolt axis. So now we are ready to use the bolt pretension object to preload these bolts. Insert a bolt pretension object. For geometry, select one of the bolts. You will notice that the bolt is being cut in the region where bonded contact is defined between the bolt and the nut. To correct this, change the coordinate system to the local coordinate system that we define. Now the bolt is split at the correct location. Apply a preload of 100 Newton in step 1. Most importantly, don't forget to lock the bolt in step 2. To apply preload to other bolts, we use the object generator and replicate the bolt pretension object for all the bolts. Now all the bolts are preloaded in step 1 and locked in step 2. Now that the model has been set up completely, we solve it. After the system is solved, in order to check whether proper sealing has been achieved, we first check the total deformation of various components. Make sure that scaling factor for deformation is set to 1 or true scale. Next, insert contact tool. We are mainly interested in checking whether any gap is created between the various parts in contact. Bonded contact pairs will never show any gap or leakage due to their inherent definition. So in the worksheet view, go ahead and unselect all the bonded contacts. Next, under the contact tool, insert gap and evaluate the results. First, let's check the status of different components in contact with each other. When we look at the top plate, we find that only the regions around the bolt head are sticking, while the status for other regions is near. In other words, regions around the bolt heads are sealed, but leakage will occur through the regions marked as near. Next, we look at the gap between various components. We find that there are some regions with a negative gap. Gap is calculated as the distance of the contact side with respect to the target side. So considering the direction of z-axis, a negative gap indicates separation between the upper plate and the gasket. We see that the regions whose status was near have a negative gap. So the recommended design change improves the sealing, but it does not meet the criteria yet. So what else can we do? Let's revisit the concept of pressure cone. We can see that proper sealing can be achieved when the pressure cones of adjacent bolts are closer. In order to increase the size of the pressure cone, one can also change the diameter of the bolt. But by what extent? Well, let's use Ansys again to run a series of simulations and pick the correct size. In order to do this, we will perform parametric study to avoid manually running the simulations for different bolt sizes. To do this, go back to the workbench window. Double-click on the parameter set to open it. Let's increase the bolt diameter to 0.9 mm and set it to current. In the project window, click on Update Project to generate the new geometry consisting of bolts with larger diameters and solve this new system. When we look at the deformation results, we see that the maximum deformation has reduced slightly. Then we look at the contact status of different components. We find that regions with a sticking status have increased in area. When we look at the gap variable, we find that a continuous annular region has zero gap between the components, indicating that proper sealing is achieved. A few small regions on the inner and outer edges of the gasket show very small non-zero gaps, but since proper sealing is achieved in regions near the bolts, no leakage will occur, and so we don't need to worry about this. Thus, by increasing the bolt diameter, we were able to achieve proper sealing and prevent leakages in the pressure vessel.